you very much again for invitation. So today the title is Volatility has to be rough, so it is something about rough volatility. So today I want to show something, some kind of equivalence between the power law type term structure with ATM volatility skew and
Masaaki, sorry, I think you doesn't show your full screen, so I think some of the words are hidden. Okay, now it's better. Yes, yeah. Now we can see the screen. Yes, now it's better. Yeah.
Yeah. Because okay, full screen is not a good idea. You mean so?
Now we can't see.
Now
the
it's okay.
No,
okay, you don't.
I think
this is okay, or
this is no. Still some words are out of the screen. Yeah. Now it's no. Probably make it smaller. I think if you make it a little bit, yeah, I think now it's fine. Yeah, yeah.
Okay. Okay. So sorry, I'm using a browser, so maybe that's why. Okay. Anyway, you can see slides. Yeah.
Yeah.
Now. Okay. Good. So let's go ahead. So I will explain what is this power law and what is rough volatility later. Then essentially, I will talk about two things. So first thing is that an asymptotic formula about the implied volatility skew. I will show that you need rough volatility to explain this power law type asymptotic power law type time structure by an asymptotic method. So this is kind of distributional property. It is essentially a refinement of the central limit theorem. And the second part is more pathwise property compared to the first one. The first one is distributional property, and second one is a pathwise property. Here I will show you that there will be an arbitrage strategy if volatility is not rough, given power law type time structure of ATM skew. So these two, from these two kind of results, I want to convince you to the volatility has to be rough under some property. So there's first kind of assumption is that the continuity of price process. So I assume the price process is continuous, and the volatility is very defined. And the second property is the power skew, I already mentioned. And the third property is no arbitrage. If you agree with these three aspects of price process or market properties, then you need to so volatility has to be rough. So this is a message of today's talk. So now, I'm not sure if can you I'm not sure because this
slide, we can see the screen. Yeah, I think it's okay.
Yeah. Okay, it's okay.
Yeah, I think it's okay. Yeah.
I'm a bit problem to kind of which part of slides I should show you. A bit anyway, okay. So now I believe you can see three figures, and so this is about implied volatility, and I downloaded the data from CBOE site about so the data is the option price, SPX option price, and I computed the implied volatility. The left one is an implied volatility, and there are several colored lines. The black one is the shortest for the shortest maturity, and the red one, green one, blue one, cyan one. So there are many maturities, and we can see that what we can see that is if maturity becomes shorter, then the the smile is more skewed, or convexity is stronger. And so if you, so I think you know the implied. I assumed you are already familiar with what is implied volatility, and so implied volatility is a function of log minus and time to maturity. The x-axis is log minus and y-axis is implied volatility. So and so different colors corresponds to different maturity, and so the lines, these curves are almost linear around the ATM. So ATM means in the log minus, this is a region of log minus close to 0. Okay, so this part is ATM, and around the ATM, or the volatility is almost linear. So you can do linear regression to find the slope of implied volatility, and this is what we call volatility skew. And the figure in the middle is plotting the skew. The x-axis is time to maturity, and the y-axis is the slope. So as time to maturity becomes smaller and smaller, the slope becomes more and more negative. The skew is stronger. So this is what we observe from here. And if you take log plot, then you have this beautiful linear fit. So what does this mean? We are essentially computing this kind of quantity. So this is a slope, and log plot is linear. So it means that this is proportional to the time to maturity to some power. And if you do linear regression to specify this exponent, then you can you observe this h parameter is almost 0. And this is just for 1 day data. So this is July 11, 3 years ago. But essentially every day you have a very similar figure. You can get very similar figure, very similar value of h. Of course, not the same every day, but always, I mean, almost all days you have value like h equals 0 or 0.05 or 0.07, something like that. So this is what we call power law skew. So the skew has this power law type structure. So now I want to explain what kind of model is consistent to this power law skew. Now I explain the mathematical framework for the first part. So I denote by S the underlying asset price process. And the Black-Scholes implied volatility is denoted by sigma Bs, and K is log minus Cs time to maturity. And I denote by E the expectation and the risk neutral measure. And I assume this is a pricing measure, which means that the call or put option price is the expectation with respect to this measure of payoff, and the implied volatility is the volatility parameter that make Black-Scholes price that coincide with the expectations. Okay, and the interest rate are assumed to be 0, just for brevity. And for the asset price process S, I assume this is positive continuous martingale under this risk control measure, and the volatility square root of V is well defined. This means that V is the time derivative of the quadratic variation of log price. Okay, this means quadratic variation. And also I define the so-called forward variance curve. This is just the expectation of V theta. V is this one. So So for the variance is the expectation of this one. So this is the deterministic curve. V theta is not deterministic, but V theta is, sorry, big V theta is not deterministic, but small V theta is deterministic. And this is what we call forward variance curve. And we want to study the asymptotics. Asymptotics mean that this time parameter theta goes to 0. So I assume that this guy is continuous at theta equals to 0. So, this is kind of minimal assumption or minimal framework. And still, we already state our first result. So this is kind of asymptotic expansion of implied volatility. We consider the time to maturity theta goes to 0. So this is short maturity asymptotics. And so not only the time to maturity is small, we need the log minus is also small. So this means we are looking at ATM. So we scale the log minus to this like this. So this theorem said that if this assumption holds, then we have this asymptotic expansion of implied volatility. So now I explain what is this assumption. So assumption is that there exists some parameter h, which is greater than 0 and less than or equal 1/2, such that this guy is uniformly integrable, and the joint distribution of these guys converge in law to some random variable. Only this assumption, we have this expansion, and the expansion coefficient alpha is determined by this limit law in this way. So it is a bit complicated, so I should explain. So, okay. Before the coefficient, I should mention about what is the assumption. So V theta is the big V theta is the variance, and the small V theta is for the variance. So the expectation, this is the expectation of this guy. So this fraction is the expectation 1, and if theta goes to 0, this is supposed to converge to 1. So H parameter determines the rate of convergence. Okay, so if there is some rate of convergence, and with this rate of convergence, after suitable rescaling, this converts to some random variable, then we have result. Okay, and for scaling for this asset price, we have square root theta, and this is a natural scale for continuous process with well-defined volatility. But this H is so you can have many. I mean, H is not necessarily 1/2. If you are considering semi-Martingale, if V theta is semi-Martingale, then H should be 1/2, as we will discuss later. But at this point, H can be smaller than 1/2. And this H actually appeared here. And now I explain what is this coefficient. So the leading term is the square root of V bar theta, and V bar is the time average of for the variance curve. And so the square root of this average for the variance is the so-called volatility index, if you know it. So the leading term is volatility index. And we have correction term alpha z. Alpha z is a function of z, and it depends on h, and depends on xi and rho, xi and eta in this form. So this is the conditional expectation of eta given xi is this value. So we have z, u, w, u, and we integrate out w and u by this way. So this is a bit complicated. I will give you some example how this can be computed. But anyway, this is the first result. And my message is that the rate of convergence of this guy, that is H, appeared here. And so this actually gives a first order correction to the implied volatility asymptotics. So how to prove this kind of result? Actually, the proof is in some sense elementary. So basically, the implied volatility expansion follows from a put option price expansion. So as you can guess, because you know the implied volatility is just inverse function of pricing function. So you have expansion of pricing, then how to say, the implied volatility is inverse function of Black-Scholes pricing function of put option price or call option price. So you have put option price expansion, then the implied volatility function volatility expansion follows. So the question is how to derive the put option price expansion. And so we consider this kind of risk-scaled put option price. So here, the numerator is the expectation of some payoff. You can look at it like that. And here, this part S0 times e to the power 0 squared theta. So this corresponds to the strike price. If you think Z times square root theta as log minus, then this is exactly the call option price. And put option price corresponding to the implied volatility, this one. And this converts to 0, so we need to scale. To scale, we need this denominator. So this is essentially the risk-scale put option price, and this can be expressed as this one. So this is also look like put option price, where delta is this kind of value. So this depends on Z and theta. And this converges to Z, right? So if theta converges to 0, then this converges to Z because of obvious reason. And here x1 theta is the risk-scaled price process. And assumption is that this converges to some random variable. So actually, so this converges to something, right? And you can see that so it is easy to it is an easy application of the martingale central limit theorem that the limit of this guy is a normal random variable. So this guy converges to normal random variable. So this risk-scale put option price converges to put option price and the Bachelier model. So this is a leading term of implied volatility, and now we want to have expansion. So we need to quantify the difference between this guy and the Bachelier price. So there's a kind of there's a well-known technique to derive this kind of expansion. So namely, we consider the heat equation, or this is a Bachelier pricing equation with this variance parameter and this terminal condition. And this is essentially heat equation. So we know the explicit solution. And because of this terminal condition, as a usual exercise in mass finance, this can be decomposed, like, I mean, using Ito's formula, this can be written as sum of this constant plus stochastic integral term and some Ito correction term. And stochastic integral term disappears if you take expectation and you only have this correction term. And if you compute the detailed terms, then actually you only have this kind of thing. And this one corresponds to Bachelier price. So this converges to this guy. And this gives you the difference between the limit partial price and this risk option price. So the expansion is given, it's obtained by looking at this one, and you assume that you will assume some joint convergence of this scaled price and also this variance or volatility. And so this is simply obtained by kind of usual dominated convergence theorem. So this is kind of elementary thing, but the result is very strong. So the expansion term alpha is a bit complicated function. So I want to have more explicit expression. And actually, in all interesting examples we have so far, this limit law of theta is Gaussian. So first of all, I explain what happens if this theta is Gaussian. So this is the second theorem. So under the condition of the previous theorem, if in addition this theta is Gaussian, then variance is, V0 coincides with the variance of Xi, and this conditional expectation is given by this. So if they are Gaussian, they have some linear. They should have a linear relation. So this explains. This is just a result of this. So this is linear in X. So the previous, so this one. So if this is linear in this guy, then you can compute this integral, and then simply you get alpha z is just the linear function of z with coefficient determined by covariance and variance of Xi and eta, and h. There are some h dependence. And once you get this, then you can get Skew formula. So Skew is, recall that Skew is the kind of derivative of implied volatility, and essentially this is a finite difference of this kind of finite difference. And you know that we have expansion of this, so just substitute the expansion. Alpha z is linear, so you just have this one. And you can see this is the proportion to theta to the power h minus 1 half. So this coincides with the power of form we observe from market data. Just a remark, although this is a finite difference form, if you add some more additional condition, assume some additional condition, then actually you can prove that the derivative is given by this. Now, more concrete examples. So there is a so-called 1/2 rule, and this is about the implied volatility skew and the local volatility model. So local volatility model is a model where this variance, spot variance, is given by a function of spot price and time. So this is a local volatility model, and so the 1/2 rule says that skew is 1/2 of derivative of this sigma. So this is I don't know who found it, but this is known more than 20 years ago, and at the beginning it was conjecture, but actually I'm not sure who was the first to rigorously prove this 1/2 rule. But anyway, we can prove rigorously this 1/2 rule. How the way is that we compute this guy. So here we take h to 1/2. As I said, if B is semi-martingale, then we should take h equal 1/2. So we consider this, and so v is this guy. So usual delta method, you can approximate this by this one, right? Because if sigma is sufficiently smooth, you can do this kind of approximation. So the limit of this guy is denoted by xc. So the eta and xc has this linear relation, and xc is has to be normal because of Martingale central limit theorem. So this is the situation where xc and eta are Gaussian. And so we can compute the covariance between xc and eta, this one, and so this is exactly this one. So the skew is 1/2 of the derivative of local volatility. Here we have S0, but if you consider the derivative of sigma with respect to log money or log price, then this S0 is absorbed. Then so you just have 1/2 of derivative. And this can be extended to the stochastic volatility model. So in the general abstract stochastic volatility model, you can it can be written like this. So here V is stochastic volatility, and V in the most of stochastic volatility model, this V is assumed to be an Ito process. And if it is a Ito process with kind of sufficiently regular behavior like continuity of these processes, then you can compute this joint distribution, the limit of this joint distribution. Actually, this is essentially the log price and log volatility, and this is by Martingale central limit theorem. Again, you can compute the limit rho. This is Gaussian. And then you can compute the covariance, variance to get this formula. So this is kind of refinement of known results, and now we can also treat the rough volatility model. And the rough volatility model, the most famous rough volatility model is the rough Bernoulli model. Where rough Bernoulli model, how to say, so I describe this rough Bernoulli model in forward variance form. The rough Bernoulli model is the infinite dimensional Markov model. Here, this is a stochastic volatility model. So we have stochastic volatility factor Vt, and Vt is determined as Vt of t. And what is Vt of S, general function? Vt of S is defined as a solution of this SDE for each S. So for each S, this is this is just SDE with time varying coefficient. And the rough Bernoulli model, we take this K as this power of type function. And so this is forward variance form, but you can have another form. So if volatility is log volatility is fractional Brownian motion, then you can derive that model in this forward variance form. The rough Bernoulli model is essentially the model where the log volatility is fractional Brownian motion. So under this model, we can compute this. This is like this as before, and this is like this, because so this says Vt of S is log normal. So this is essentially like Black-Scholes model. So this is log normal. So we can approximate this by this normal random variable, and then the limit is easy to compute. So the difference is that we need this scaling factor. So we need theta to the power h. H appears here. So this k function has a singularity. So we need some function which absorb this singularity. So here we have theta h. So the limit h. So we have this power rho. In the previous case, h equal 1/2, so this part disappeared, but now we have h dependence. And if h is very small, then this is consistent to the market, as I explained before. Okay, so there's a remark about the skew stickiness ratio. So Lorenz Bernoulli's paper 2009 introduced the so-called skew stickiness ratio. So it is defined as the ratio between covariance between volatility and log price and this skew, volatility skew times this variance. So formally, from our assumption, under our assumption, this can computed like this. This can be approximated by like this, and this computed as this one. And then this actually suppose some computations in the formal computation in the Bernoulli paper. And so in this paper, a time series plot of the SSR is given, and this also indicates h is close to 0, and this is consistent with power or skew. So this is another evidence of rough volatility model. And I already talked 30 minutes. So far, what we observed is that the rough volatility model explains the power of skew. So in particular, the power of skew is compatible with arbitrage-free models. And the key parameter h was determined as the rate of weak convergence of the spot variance. And fractional Brownian motion WH with Haas parameter h has this rate of convergence. So that's why a rough volatility model can recover the power. And at the same time, the reason why we call such kind of model rough volatility model is because such kind of fractional Brownian motion has rough path, meaning that it has Herder regularity with Herder exponent h. In the semi-martingale or Brownian motion, the Herder regularity is essentially 1/2, but fractional Brownian motion, this parameter is h, which is smaller than 1/2. So the path is rougher. But from this kind of asymptotic analysis, the deviation between this roughness and power rho is a bit indirect. I mean, fractional Brownian motion has both property, this rate of convergence and pathwise regularity, but this is kind of indirect connection. So my question is, can we relate more directly the roughness of path to the power rho? And so this is the topic for the second result, and the actual answer is yes. So this is a framework for the second part. Now I fix maturity capital T, and still time to maturity theta goes to 0. So it means that now the current time T converts to capital T. And so I change notation bit. So the market implied volatility for strike K at time T is denoted by the sigma BST K. So now T goes to capital T. So this is a kind of stochastic process. And now we need to formulate or describe. We need a kind of mathematical description of what is the power of skew. So this is one possible definition of power of skew. So for h in between this interval, we say the h power on the negative volatility skew holds if there exists adapted process sigma and alpha such that some property and this property. So this is a bit complicated, but essentially this is description. This is mathematical formulation of power law. So here we have theta to the power h minus 1/2. So this is essentially this is the most important part, and yeah, we allow some negligible part or smaller noise or smaller part, and we only need to look at the ATM. So the the strike price is supposed to be sufficiently close to the spot price in this sense. Okay, so the spot strike price is close to the spot price in this sense. So this is our formulation of power law. So now we see what happened under this power law skew. And before that, I need a lemma. This lemma says that the Black-Scholes delta hedging error is small. I mean, not small, not necessarily small, but Black-Scholes delta hedging error is only of this order when a volatility is H0 error. So so the formal description is like this. So if F is a positive continuous semi-martingale with this variance, spot variance, and this spot variance is H0 header, namely these guys. This guy is finite almost surely. Then when you do Black-Scholes hedging of this kind of call option or this kind of put option, then the hedging error is of this order as the starting time of hedging close to the maturity. So this is a similar. This is a similar result to the previous asymptotic result. So essentially, as you know, the hedging argument is kind of PD argument. One way is just to consider the PD with this terminal condition and do Ito's formula, and then you get the price and the hedging ratio, and the remainder part is disappear if model is correct. And now this is stochastic volatility model, and the Black-Scholes model is not correct one, so we have some error, hedging error, but this is small when the current time is close to time to maturity. And how small depends on the regularity of volatility path. So this is what it is. This lemma says. The hedging error is of this order. And so this is call option, this is put option, and combining this, yeah, you can get this one. So here, put option, call option, and this specific weight corresponds to the put call symmetry, so-called put call symmetry. There's a famous paper by Peter Carr and Roger Lee about this put call symmetry, saying that with this special combination, the Black-Scholes price is same. Black-Scholes price for this and this are the same. So if you consider this portfolio, then the Black-Scholes price is 0, so you don't have constant term. And this is the hedging term, and the hedging error is of this order. So this is a kind of preliminary result, and using this as now we construct arbitrage strategy. So arbitrage strategy is something. Okay, I will explain. So now I define the building blocks of an arbitrage strategy. So now we consider the sequence of time tau n. So this is t minus 1, capital T minus 1n. So this is maturity. So this is the time step, time point converging to the maturity. And we choose strike price. So that this is sufficiently close to the spot price in this sense, but not too close to stock price in this sense. And now pi n, denoted by pi n, the P&L of 1 unit short-term put option is like K tau n, and K divided by S unit long of the call option is like this way. And so I do the Black-Scholes delta hedging. So this is a price not put. So I short this put option. So I get this put option price, and I long call option with this unit. So I pay this money, and this is short. So I need to pay back this option payoff. I get this option payoff, and I do delta hedging. So this is the delta hedging P&L. And there should be some hedging error from this kind of portfolio. And this hedging error is denoted by pi n. Okay. And so according, okay, the theorem said that suppose the h power on of negative volatility skew holds. Okay. And suppose S is a positive continuous semi-martingale with this spot variance being positive and H0 held almost surely. And suppose H0 is greater than H, then this combination of portfolio P&L becomes infinite. So what this means? So if H0 is greater than H, if regularity of volatility path is better than the value which is indicated by the power law, then you have arbitrage. So this means you have infinite profit. Okay. So the idea is quite simple. So I already explained, if the volatility H0 held a continuous, then the Black-Scholes delta hedging error of the specific option portfolio in the nth building block is only of n to the power H0 minus 1/2. So this is what we stated as lemma, as a preliminary lemma. And the Black-Scholes price of the portfolio is 0 due to the put call symmetry of Carr and Lee. And on the other hand, we assume power of skew. So power of skew means the market price is not 0, but of this order. So this is hedging error, but this is the market price. So you can get this and you lose this. So decoding that this one is infinite, but this one is finite if H0 is greater than H. So this using this weight, the profit. So just a minute. The market value you can get from this portfolio is infinite, but the hedging error is finite. So the total you have infinite profit. So the implication is that H0, the held regularity path cannot be higher than H. So if you have power law in the market and H is small, H to close to 0, then you cannot have a better regularity, header regularity than the value close to 0. So it has to be zero. So this is the message of my talk. So here are some concluding remarks. So the Bergon paper also have similar idea, and he constructed an arbitrage strategy. But his case, his strategy exploits the difference between the SSR, which was H plus 3/2, and so empirically this is H equal close to 0, so SSR is close to 3/2. But or at that time, people believed that the volatility has to be semi-martingale. So theoretically, people believe that this SSR has to be 2. So H has to be 1/2. So this has to be 2. So the Bernoulli's idea to take or exploit the difference between this SS value, empirical SS R value, and the theoretical SS value. So this was the idea of Bernoulli's arbitrage strategy. So our strategy is simpler, and exploit the divergence of the how to say, the exponent of the power law. So the strategy is different. And the volatility is indeed statistically estimated to be rough. So you can look at my paper or as a paper. And also the famous paper by Jim Gatherer and Mathieu, the title Volatility is Rough. This paper shows a rough volatility model has a good predictable performance. And also there is a paper by Mathieu and co-authors using the Hawkes type microstructure models to derive rough volatility as a scaling limit. And it's in particular in this Paul Jocelyn and Mathieu's paper derive this scaling limit. I mean, okay, let's say that this kind of scale limit is like this. So you assume the kernel of Hawkes process is like this. Then you have a power run volatility or something like that. So the question is why the kernel function of the Hawkes kernel has to be like that. And this paper by Paul and Mathieu showed that actually this kernel, heavy tail kernel, is derived via turbulence theorems by assuming the existence of a scaling limit and market impact function. So somehow explain this kernel by market impact modeling. So our way of reasoning the rough volatility is different from this one. So we are more simple. It can be more simple that we just assume power law, and then you have to have rough volatility. Okay, so this is my talk. So this is the end. Thank you for your attention, and I welcome questions.
Okay.